Hello, everyone. All right, so today we are going to combine two things we've been doing that I've tried to get you to see the connection in the discussions. We're going to tie together area under the curve and the definite integral. And I'm guessing some of you have kind of caught on that the definite integral is a way to find the exact area under the curve. I don't really go into the proof of why in this class. I do that more in Calc BC because there's a little to it, not a lot, but down the road, I may show some of you how it works. But really, the thing to take away is the definite integral gives the exact area under the curve. So I'm going to do a bunch of examples on this that still show why we still need Riemann sums and all these other things, and a couple of other important topics that we haven't seen yet. So the first example I'm going to do is I'm going to give you this function, x squared minus 4. We're going to approximate the area, this curve, using 4 subintervals from, and we're going to go 0 to 4, because something's going to come up that we haven't talked about yet that we want to be aware of. And rather than sketch it this time, I'm just going to cheat and use Desmos. Here's the graph of it. Notice this one goes below the x-axis. So how can I do and the first way I'm going to do it, I'm going to go left-hand Riemann sum. Okay, so 4 subintervals. The base is always going to be on your x-axis. That's not going to change. So we're still going to have 4 rectangles, but the way you draw them is a little bit weirder. So follow my logic here. If we're doing left, remember how it works. You start from left to right. And typically before we would go up to the curve and then over. Well, the curve's down this time, so we're going to go down to the curve, hit the curve, and then go over and then back up. That's our first rectangle. The next one, same thing, starting from left to right, down to the curve, over, back up. Our second rectangle. Our third one, to the curve. Now this one's a little weird because we're already at the curve, over and back down. So this is one of those cases where you're going to get a 0 area. And then the last one's like normal, starting from the left point up to the curve, over, and down. So that's what your 4 rectangles would look like in this case. So what happens when we calculate these areas? Let's talk about this blue one first. The area of the blue one is a base of 1. That's not going to change. Something's different about this though. Remember how I got these heights earlier? I would plug in f of, in this case, 0. Well, if I plug 0 into this, I get f of 0 is -4. So my answer is -4 for that rectangle. Is that a thing? Yes. You can have negative area. Negative area means below the x-axis. You should always get negative area when you're below the x-axis. We're going to see that a lot in some of the examples I do today. So in geometry, if you took geometry, you may have heard that area is never negative, because when you're talking about area, it's a geometrical idea. I mean, this is kind of geometry, but we're going to really be using this for something called accumulation, and you can definitely accumulate negative area. So just keep in mind that if it's below the x-axis, it's negative area. So same thing with the next one. This one, the area is base of 1 times, however we got this height, and this height was f of 1, which was, when I plug 1 in, I get -3, so -3. And then finally the last one, this area is base of 1 times a height, and we got this height by plugging in 3 to the function, and that gives me 5. And yes, that's positive area. So what is our area approximation? It is the negative area plus the negative area, sorry, I'm out of order, let's try again. The -4 plus the -3 plus the 5. And yeah, some of the negative area actually cancels out the positive area. So we do get -7 plus 5, which is a net area of -2 in this approximation strategy. Okay? So, yes, you can have negative area combined with positive area, and the total is going to be some combination of the two. All right, let's do a right-hand Riemann sum. So I'm going to erase all this. This is a case where I'm really going to be clean with my graph so you can see it all. So a right-hand Riemann sum. Same thing. 1, so just rectangle, 2, 3, 4. But this time starting from the right and going left. So I'm going to start all the way from the end of my interval up to the curve. Up, right to left. Beautiful. Up to the curve, right to left. Up to the curve, it's already on the curve, right to left, so that's a 0 case. Up to the curve, but this case it's down, right to left. So I'm adding up these 4 areas, and in this case, one of them is 0 again. So in this one, it would be the base length, 1 times, and some of you in your homework caught on that there's kind of a formula to this. It's like we plugged in f of 4 plus f of 3 plus f of 2 plus f of 1. Sorry, can't see that. Let's bring it down. There we go. And that gives me 1 times. F of 4 is 16 minus 4 is 12. F of 3 is 5. F of 2, we already found, is 0. F of 1, we found earlier, is -3. 17 minus 3 is 14. So a pretty big difference because, well, we're including this big positive area rather than an extra negative area. But that's why we have these different approximation strategies. Okay, let's do a trapezoidal. Trapezoidal and midpoint are typically the better ones. They're more accurate. So let's do a trapezoidal. Trapezoidal says, again, we have these 3 bases. This is where you're going to have to kind of focus more on how the calculation is going to work rather than the weird shapes you're about to get. So check this out. Trapezoidal says go from here to here. No problem there. This one's still kind of fortunate because it comes back to 0. If it went to the other side of the axis, though, we would literally be connecting them on both sides, which is why I say just stick to the formula. So when we do our trapezoidal, we know it's 1/2 times the base times. Think about what each of these trapezoids is going to be. I'll draw all 4 of them real quick. This one looks like this. And then this last one looks like this. Okay, so how do we get the first trapezoid? It's this base plus this base. So f of 0 plus f of 1. How do we get the next trapezoid? Well, it's this base plus this base, which is just f of 1 plus f of 2. And yeah, I can actually put them all together. It's kind of like I factored out the 1/2 and the 1, which is in common between all of them. How do I get the next one? Well, it's just f of 2 plus f of 3. How do I get the last one? Well, it's just f of 3 plus f of 4. Add them all up. So this gives me 1/2, 1, times f of 0, which is -4, plus 2 f of 1s. Look, there's 2 of them. So f of 1 was -3 plus -3. F of 2 was 0 plus 0. F of 3 is 5 plus 5. F of 4 is 12 plus 12. And what does that give me? Let's get this out of here. -4 plus a -3 is -7, -10. But adding 10 more, back to 0. 12 plus 12 is 24, divided by 2 is 12. And yeah, -4 plus -3 plus -3 plus 0 plus 0 plus 5 plus 5 And 12 plus 12 is 24 times the half is 12. And that's that. Ooh, one sec. Oh, no. Okay. I made a mistake again. There's not 2 f of 4s, there's 1. So half of 12 is 6. Okay. Again, man, I remind sometimes. Okay. Because there's only 1 f of 4, not 2. How did I know I was wrong? Because I knew the next thing I wanted to do. In the performance task, I asked you to realize something. I think it might have been the homework. I can't remember. Check this out. If I add these two things together, so -2, start out the time here, -2 plus 14, I get -12, divided by 2 is 6. The trapezoidal is always the average of the left hand and right hand. So if I take the left hand, right hand, add them together and divide by 2, you always get the trapezoidal. It's because really we're adding the same numbers together. So at the end of the day, you can add the left hand and right hand, divide by 2, and save yourself a little bit of work to get the trapezoidal. Only works if you have the same number of subintervals for all of them. Okay. And finally, the last one is the most obnoxious one. Midpoint. I say obnoxious because we have to find the halfway points. So again, we're still going to have 1, 2, 3, 4. But in this case, the height of them is the halfway point. Right there. The halfway point, which is about here. The halfway point, which is about here. And the halfway point, which is here. And then we got to add these up. So that would be the base length of 1 times f of 0.5 plus f of 1.5 plus f of 2.5 plus f of 3.5. And this is where I'm going to do what I showed you the other day, where I'm going to cheat a little bit, bring in Desmos. I already defined the function. You can do f1. Sometimes that'll be helpful. Sometimes sometimes f of x will be helpful. Sometimes you can even do f1 of x. And then tell it the values you want. So I want it to find, I'm actually not going to use one here. I want it to find f of 0.5 plus f of 1.5 plus f of 2.5 plus f of 3.5. And gave me an answer of 5. So that's pretty close to 6. So I know my answer is somewhere between 5 or 6, probably, because usually the one is an over approximation, the other is an under. So I know the answer is probably somewhere in the neighborhood of between 5 and 6. Which is an over and which is an under? I mean, you can kind of tell just from the answers you got, but how do you know in terms of what the graph is doing? Since it's increasing, but it's negative and positive, the same rules don't exactly apply. The entire thing has to be positive for you to use your over and under approximations. So long story short, I'm not going to ask you if this is an over or under when either the graph changes from increasing to decreasing, or if the graph is below and above. I'm not going to ask you about over or unders because it's less uniform. There's not a specific answer depending on situation. In this case, you'd have to analyze how much of it is below the x-axis and how much is above. And we're not going to do that in this class. Okay, so the moment we've been waiting for. These are all approximations. Is there a way to find the exact area under the curve? Yes, it is called the definite integral for reasons. In BC, I prove it to you. If you're dying to know, I can prove it for you a couple ways. One way is to add up infinitely many skinny rectangles. Another way is to do a little slick maneuver with an area function. We're not going to do that right now. We'll do it next year if you have me in BC. The point is, to find the exact area, all you have to do is do a definite integral with your function. So it would be the area you're looking for from 0 to 4 of your function, f of x dx. That's it. So you can either do it by hand. So 0 to 4 of x squared minus 4 dx is x cubed over 3 minus 4x from 4 to 0. And then plug in 4. 4 cubed over 3 minus 4 is 64 over 3 minus 48 over 3, which is 16 over 3, which is 5 1/3. Well, it's not approximately, it is 5 1/3. Is that between 5 and 6? Yeah. Does it seem legit? Probably. And then if you want to really make sure, which you should always do, start getting used to doing this, because we're actually going to use Desmos a ton for this. Ready? We're actually going to be doing this a lot. Ready? Int 0 to 4. And check this out. You can just type f of x dx. Start getting used to this in Desmos. Define your functions and then call them up when you're using them. You don't have to keep typing x squared minus 4. You can just refer to them. You define them and then you refer to them. So a lot of what I'm doing in this problem is going to be how we approach the more sophisticated performance tasks in pre-response. All right, so we have this method that literally does find the exact area under the curve. It's pretty cool. There's a way to do this where you shade too. I can't remember how to do that. But that finds the area here and all the way up to here. One thing, we just said that the area under the curve is negative if it's below the x-axis. So this area right here, so we can test that theory and see, does it really give me a negative area? Yeah, so it turns out that this area right here is negative, like I said, 5 1/3, which if you count the little squares, 1, 2, 3, kind of like 4, 5, and a little extra. Yeah, it looks legit. Looks like it actually is the answer. Okay, so why do we care about this? Why does this matter for anything? Well, think about back to your days of geometry. You learned how to find the areas of things like rectangles and squares and circles and a few things. But what if I wanted to find the area of something else, like an oval? So in real life, what if I wanted to find the surface area or area of a rectangular patch that looks like this? A rectangular oval patch that looks like this. What if I'm building a swimming pool and I want to lay concrete, above ground swimming pool, the height of class, and I want to put concrete down in an oval, and I got to know how much concrete to buy. Well, if it's me, I would just buy extra and then return what I didn't use. But some people can't do that. What if this is a billion times bigger than that and you millions of dollars on the line? Point is, there's more precise ways to do this. One of them is you can be smart and design a function and then find the area using the area under the curve. My dogs are freaking out. So watch what I can do. I'll get to that table in a second. I can define a function. I'm going to call it g of x. And I can make it into a curve that I know will look like an oval. How about 4 minus x squared divided by 9? Check it out. There's an oval. It's only half the oval, but I can find this area under this curve and then just double it. So if I do int, looks like it goes from -6 to 6 because I want to find the area from -6 to 6. Call up my function. Bam, 18. Does it look like 18 is a legit answer? Well, if this is counting by ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, and change, so a little less than 10. Yeah, it looks like 19 is about valid. And then just times 2. So this answer, check this out. Control C, Control V times 2. Fancy. That gives me the area of this oval. You can do it with anything. I can come up with any curve. I could literally take my hand, come up with a curve that, well, I guess it has to be a function. Map it, which is a thing. We haven't learned how to do that in this class. You won't learn that until more advanced calculus courses. But then you could just calculate the area under it, and that's a way to get surface area things. And that's just one of the crazy things we're going to be doing. So this is a pretty cool strategy to find exact area very easily. You don't even have to memorize formulas. So going back to the area of circles, for example, let's get rid of this 9. Why is this undefined? Because the graph doesn't go to -66. That's a domain issue. Semicircle, right? The area of a circle is pi r squared. So if I wanted to find the area of this circle, I would just have to double up this area. And the radius looks like 2. So it would be pi times 2 squared, so 4 pi. So if I do the integral of this from -2 to 2 g of x dx, and I double it, what did I say this was? It should be 4 pi if it's a circle. No more formulas. If you know calculus and you can fit a function to it, you can do this for everything. If you really wanted to be annoying, you could even do something like a rectangle. So what if I have a rectangle and I drew a straight line and I found the area under it from 0 to 4? The area under this from 0 to 4, which makes a square, from 0 to 4. Come on, 4. 16. Yeah, it is. So there you go. No more formulas. You can just use the area under the curve of a function. Much cooler feeling, I guess. Okay, the last thing, and then the question you should then have in your mind is, why on earth do I need to then use Riemann sums or approximations if this strategy finds the area under all curves? It seems like I can always find the exact. Yeah, it's true if you have the equation, but sometimes you're not going to have the equation. Sometimes you're going to have a table of values instead. So check this one out. Copy this table down. I'm just going to come up with arbitrary values like 1. Come on. All right, whatever. Start over. By the way, to make a table in Desmos, you come here. How do I do this? Oh, g of x. Say. I can't remember how to do this. Oh, wait. Table. There we go. Type in the word table, and it pops up a table, and then you can call this whatever you want. So now I'll call it G. All right, so let's go 0, 1, 2, 3, 4, just to keep it pretty simple. And let's do some values of like 3, 1, -2, 4, 6. So we have incomplete information. We have a table that represents a function, but we don't know what's going on outside of the values that we're given. So what do I mean by that? Well, here's what I mean. Let's do this. Let's do a full screen snip. And let's talk about this. We don't know what the function's doing. So in reality, the function could be most likely doing something like, oops, I went lower than I wanted, didn't it? Let's try that again. Here we go. Full screen snip. The function could in reality just be going very simply like this. Maybe it has a critical point right there. That's one case. Or maybe it's not doing that at all. Maybe it's doing something like this. Point is, you don't know. There's a lot of information you don't have. So when we do Riemann sums like this, when we find the area under this function, we're just going to kind of take it as the best case scenario, and we're just going to use an approximation and assume everything's relatively straight connected. So yeah, you can draw a smooth curve just so you don't confuse yourself about differentiability, meaning don't make cusps. And let's just do a left-hand Riemann sum to find 0 to 4 under the curve with 4 subintervals. Well, once you have the graph, nothing is different. So if you look at the graph and try to do it graphically, once you've drawn the points, do everything like normal. We're going to have one rectangle here. We're going to have one rectangle base here, one rectangle base here, and one rectangle base here. Up to the curve, left to right. Up to the curve, left to right. In this case, the curve's down. So down to the curve, left to right, up to the curve, left to right. And you're always hitting those points, the concrete points you know about. And then just find the area of each of these rectangles. So you can find Riemann sums with tables. And we're going to be doing that a lot because sometimes we don't have the function. We won't have the actual equation. All we'll have is a table of values, and we'll have to do an area approximation. That's all we can do. So when you get really good at this is the last thing I'm going to say. When you get really good at this, you won't even have to draw the graph. So if I were to look at this table and do a trapezoidal with 4 subintervals, I would do something like this. I know it's 1/2. Since it's 4 subintervals and it goes from 0 to 1, 1 to 2, 2 to 3, and 3 to 4, I know the base is 1. And the trapezoidal just says this. Start with this one. Plus. That's base 1 plus base 2. Plus, and then move on to this. Base 2 plus the other base. And then these two. And then these two. And that's it. And then add them up. 6 plus 4 is 10, 14, back to 10, 12, 15 divided by 2. Approximately 7.5. Okay, so long story short, definite integrals give exact area, but we still have to know our Riemann sums and our approximation strategies if we're given tables, which we definitely will. And sometimes we'll be given a graph, and we'll have to do kind of what I did earlier, where we'll have to know things about the formulas. So even though I said you don't have to memorize the formulas, you kind of do. You have to know the area of a circle and a rectangle and a triangle. We'll get to that later. That's not happening today. All right, that's it.